In the video where we looked at the natural transformations that exist between contravariant home functors, we saw that we could exactly categorize what the natural transformations possible were, and we could actually describe them fairly in detail. We're going to follow a very similar argument in this video. However, in this case, we're going to generalize by one step by, instead of having a home functor on the bottom as well, we are just going to have an arbitrary functor f going from our category C still into the category of sets. So the top functor is still the same, it's still the contravariant home functor, but now instead of also having a contravariant home functor on the bottom, we're just going to have any arbitrary set valued functor on our category C. So let's imagine again that we do have some sort of natural transformation, which is a collection of set functions going from the home sets all going into A. So the contravariant home functor has our target object A, which exists in the category C. And every domain of these natural transformation components is a home set going from some object in C into our target object A. And of course, for these to be components of a natural transformation, we always need this chain to commute with this chain, which is lambda C after precede by F is equal to f of f after lambda d. We then noted that any of the morphisms that exist in any of these home sets are going from some arbitrary object C to our target object A, and all of those morphisms exist in the category C. So we said what we actually could do is that we could take a look at what this looks like for one of the morphisms in one of these home sets, because all of the morphisms in all of these home sets, which remember are the domains for our natural transformation components, they all exist in the category C. So let's try that. Well, now we have some object C and a morphism F going from C into A. This now becomes the home set from A to A, and this becomes the functor F applied to A. Of course, this component now also has to be the component for A, which makes sense because A is in the category C, so there needs to be a component for A as well. The naturality condition simply changes to have an A here. This is the component for A now. So we have that again, lambda C after precede by F is the same as f of f after lambda A. But we said last time that we know that there is something in the home set from A to A. So we don't always know that there is something in that home set, but in this case we know there definitely has to be, which is 1A. So we can, in this case, say that the naturality condition must also hold if we apply this equation to the identity on A. Well, if this is the case, then we get that lambda C after 1A after F, simply applying precede by here, is equal to f of f after lambda A of 1A, which is equal to lambda C of F equal to f of f after lambda A 1A. But this was for an arbitrary f and an arbitrary c. So what is this expression actually telling us? It's saying, well, the natural transformation component for any object applied to any morphism in that home set, which is the domain, is only dependent on what we assign to lambda a 1a. What does lambda a map 1a into in f of a? And every single component is going to look the same. It's just going to be f of f after lambda a 1a. So what we've established so far is that if there is a natural transformation, so we don't know that there's a natural transformation between these two, but we know that if there's a natural transformation going from the contravariant home functor with target object A to an arbitrary set valued functor f, then it must look like this. All of the components are the same, and all of the components look like this, completely determined by the value of lambda a1a. Whatever object in f of a, lambda a1a assigns, is completely determining that natural transformation. So, two questions we can ask ourselves is, first, is this actually a natural transformation? We can say that if it is, it has to look like this, but we need to still establish that this is actually a natural transformation, because it could be that it has to take this form, but this isn't one, so there's no natural transformations. But as we'll see, that's not the case. This is a natural transformation, and we'll look at that. And the other question is, how many ways can we do this? How many ways can we assign lambda a1a and completely determine a new natural transformation? So the question we might ask ourselves is there a bijection between the objects in f of a and the natural transformations between these two functors? To investigate these questions, let's suppose that x is an arbitrary object in the set f of a, which exists here in this category of sets. And let's adjust this diagram to go back to an arbitrary morphism in C rather than just morphisms which exist in these domains. So everywhere we had A, we replace it with D again. Our naturality condition again gets replaced by D here. And the question we want to ask ourselves is, if we simply take every component lambda c applied to f as f of f applied to x, so we just fix that x in f of a, and we just say every single component is just f of f applied to our fixed object x, then does this actually give us a natural transformation? So let's take the left half of this expression, lambda c after precede by f. Well, the object that we apply this to is a morphism in the home set from D to A. So suppose we have some morphism D going from D to A. Then we get, by applying precede by, that this is equal to lambda c of D after f, which is, by this expression, just f of D after f applied to x. And since this is a contravariant functor, when we break this up, we need to flip the order. So we go f of f after f of D applied to x. But f of D applied to x is just the component for D of our natural transformation, or the function that we're trying to check whether or not it's a natural transformation. So this is lambda D applied to D. And so there we go. We have our naturality condition satisfied. lambda c after preceded by f is, for any d, is the same as f of f after lambda d. But notice that this x was completely arbitrary in f of a. So it doesn't matter which x we pick in f of a. If we use this definition for the components, we will get a natural transformation. So what we can say about that is that if we look at all of the natural transformations from our contravariant home functor, home blank a, to the functor f, and we map that into the objects in f of a, then we get, say if we call this phi, then we get that phi is a surjective function. It will work for any of the x's in f of a. That is, this mapping is surjective. But this mapping phi is also clearly injective, because if two natural transformations both map to the same x in f of a, then they're both going to be defined in exactly this way, so their definitions are going to be identical in every single component, and so they're going to be the same natural transformation. So we get that phi is both surjective and injective, which means it is a bijection. But we're working here in the category of all sets, and we know that bijections in the category of sets are the same as isomorphisms. So if we think of these two objects here as objects in the category of sets, then we can actually say that these objects are isomorphic. It turns out this is actually a very famous and important result from category theory called Yoneda's lemma. And in this case, we've looked at the contravariant version of Yoneda's lemma. There's also a covariant version, which looks at covariant home functors. But to state it all at once, let f be a functor from a category C to the category of sets, otherwise known as a set-valued functor. And in this case, we just need to be careful of one detail, which is that most of our proof took place in the category of sets. So we need all of the home sets in C to be objects in the category of sets. That is, we cannot have pure classes as home sets in C. So we don't allow that in our discussions, but just in case you are working with categories where you can have pure classes as home sets, you cannot do that in this case, because obviously most of the proof won't work because your home sets will not be in the category of sets anymore. So let f be a functor from a locally small category C to the category of sets. Then the set of natural transformations going from the contravariant home functor for any object A to our functor f is isomorphic to the set f of A. Moreover, we can actually explicitly define the bijection between these two. So not only do we know that there's a bijection, but we can actually define it, and it's given by the expression on the bottom. So phi of a natural transformation lambda is just going to be associated with whatever lambda A, the A component for lambda, assigns to the identity morphism on A. That will be the object in f of A that we are associating that natural transformation with. So this is quite a striking result, because just by defining what a natural transformation is, we don't necessarily know for any given functors what the natural transformations might look like between them, or even how many there are. But in this case, we can say a lot about the natural transformations going from contravariant home functors to set-valued functors. And remember, this is for an arbitrary category C and an arbitrary set functor F. So this applies to a lot of situations, and it quite in detail describes what those natural transformations look like. And not only that, but we can line them up in correspondence one-to-one with the objects of f of A, which often we'll know quite a bit about because it's just a set in the category of sets. So that is Yoneda's lemma. It has many important corollaries and many other associated results in category theory.